Trey is the co-author of the book Solar in Action. And you can imagine from the title of the book that his talk is about intelligent search. So please enjoy Trey's talk and make sure to ask him lots of questions. He's a very brilliant guy, and make sure to ask him all the questions you have about search. Trey, please go ahead. Let's give a big hand to Trey.
Please use the first one. Where is it? The one that's
this. I can just use this.
okay.
Okay, very good. Thanks everybody for having me. I really like this questions on Twitter thing, but I'm not going to answer live. But I also have a lot of material to get through. So what I do have is a book, copy of my book I'm going to give out to somebody. But I think since I won't have time for questions, post your questions on Twitter and I'll hunt you down later if I like your question and give you a book. Okay, so yeah, the title of my talk is Intent Algorithms, the Data Science of Smart Information Retrieval Systems. As Khalifa said, I'm head of engineering at LucidWorks, formerly director of engineering at CareerBuilder, graduated, got my master's at Georgia Tech, and more recently studied search basically at Stanford. This is the agenda. I'm probably not going to get through all of this. I'm going to do a quick poll just out of curiosity. Who in here has a decent background in information retrieval? Okay, that's more than I thought. Who in here's used Lucene or Solar or Elasticsearch? Awesome. Okay, I can go fast through the beginning materials then. Okay, so I'm going to quickly talk about Solar, give you guys an introduction. I'll go quickly through that. Also talk about my company LucidWorks and what we do with Solar. And then I'm going to quickly cover some search engine fundamentals, sort of how keyword search works, relevancy ranking, domain-specific relevancy and functions for that, and how to really cater search towards domain-specific needs. And then talk about reflected intelligence, which is this idea of sort of feedback loops and the system learning and getting more intelligent and more relevant over time. And then finally, with whatever time's left at the end, I'll touch on semantic search a little bit. So this is my general kind of overview of how I think about relevancy. When you go to a search engine or you're dealing with a recommendation engine or any time you're looking for data, there's different ways you can the data can come to you. One is through traditional keyword search, which is the upper left-hand circle, where people come and they enter keywords or enter in a description of what they're looking for. A little bit higher up on the right, there's this idea of recommendations, which is, based upon what I've done before and what you've learned about me, show me things that might be interesting. Those aren't two dichotomous things, however. There's a heavy intersection in between, which is when I run a search, show me things that are what I searched for, but rank them based upon how relevant they would be to me based upon what you know. And that's this idea of personalized search. In the bottom circle, you've got this idea of semantic search, which is more along the lines of understanding a domain. So if I type in, the word driver, does that mean a truck driver, an Uber driver, kind of golf club? Does that mean a hardware or printer driver? Like, depending upon who I am in the context, or maybe the domain that I work within, there can be a different meaning for that. So semantic search is this idea of trying to understand the context in which the words and phrases appear and what that meaning is. And then, if you sort of take all of these areas together, hopefully the intersection is really understanding the intent of the user based upon their context, the content they're looking for, and an understanding of the domain. So what do? I work at a company called LucidWorks. We are the primary commercial sponsor with the Apache Solar project. So it's an Apache project, completely open source, open community. We have the largest number of committers of any company, and we invest very heavily in it. And we do consulting around solar. At the end of the day, we're a search company. We do search-driven everything. We've got over 300 customers, between solar and our commercial product Fusion, and we help customers deliver relevant search at high scale. A lot of you guys have heard of Apache Solar, which is awesome. If you haven't, Solar is the popular, blazing fast, open source enterprise search platform built on Apache Lucene, according to the internet, which I believe. Some key features of Solar include multilingual keyword search, relevancy ranking of results, so you get hopefully the most relevant results at the top, faceting and analytics, keyword highlighting, spell correction, autocomplete, sorting, grouping, deduplication, geospatial search, complex function queries, content-based recommendations, the ability to do graph queries and graph traversals, the ability to execute SQL queries against the search engine and get the results in ranked order back, streaming aggregations, and a highly configurable plugin framework, machine learned ranking built in, and I'll show you guys an example of that in just a bit, as well as the ability to on the fly issue queries to generate machine learning models and use them on your search results. So people who are doing really sophisticated IR things are often doing them on Solr, more so than any other platform. Solr is also the standard for enterprise search with over 90% of the Fortune 500 using it. So at LucidWorks, we invest very heavily in Solr. We also have a commercial product called Fusion, which basically is Solr plus everything else that every company builds over and over again that keeps them from getting to business value. So what we found is that 80% of a company's time is spent building plumbing and architecture just so that they can get all the data where they need it to have relevant search. So this red box in the middle is Solr, but to have a really good system, you need to attach either Hadoop or Spark to it or something like it. You need Zookeeper, you need some sort of an admin UI scheduling, and then there's a lot of things you have to do yourself, like build connectors or use open source connectors to pull data in, relevancy ranking tuning, implementing security, deployment, monitoring, all of these things that are just a lot of engineering work. We've done for customers, and so we sell an out-of-the-box product. This is end-to-end platform for building data-driven applications, whether that's search, recommendations, or analytics. So I won't go into everything that we add on top of Solr, but we have a lot of happy customers, and our Fusion product powers many of the best and brightest companies in the world. So it's really fun to be able to solve really hard and fun search problems, which is what I'm going to talk with you about today. What does it mean for a search engine to be relevant, and how do you get there? So how do you understand user intent? And this is a spectrum, is sort of how I think about the maturity of an organization when it comes to search. So at the bottom left corner of the spectrum, you've got your basic keyword search, which is what you get out of the box with Lucene or Solr or Elasticsearch. You get TF-IDF ranking, an inverted index, some text analysis and NLP capabilities, and that's about it. And that's where most people start, and unfortunately where a lot of people end. If you go further up the spectrum, you start getting into domain-specific understanding with things like taxonomies, entity extraction, and building out ontologies and maintaining good synonym lists. As you keep going, you get into query intent, which is understanding what kind of query this is, parsing it out into words and phrases that are meaningful in the domain, expanding out to do more of a conceptual search instead of a text search, adding domain-specific rules, clustering, classification, those kinds of things. And then, as you keep going further, you get into things like signals, which is when users take action on a document, whether they click on it, maybe they purchase something if it's e-commerce, maybe they apply to it if it's a job posting, or maybe they save it to a folder or send an email. Those signals are very meaningful, and they give you an indication of what users actually care about in terms of your content. And those signals can be used for things like generating recommendations, or even just for boosting up the most relevant documents for a query. You also get here into things like multi-arm bandit, A/B testing, learning to rank, and I will show you again an example of that shortly. And sort of the holy grail for me is taking the signals and the feedback from users and feeding it back into the system, so that a lot of these areas aren't things that people have to spend years and years building out manually. Like, if you're building taxonomies or ontologies out, that's very expensive and labor intensive. If there's a way to do that automatically, just based upon the feedback coming in from users to the system, that's ultimately what I would like to see. So to me, a lot of these areas can be automated away, and that's something I'll talk about throughout the course of the talk. So basic keyword search, a lot of you guys know this already, but a search engine is fundamentally powered by something called an inverted index. Whereas normally when you have a database, you would have a document ID and then a content field with all the data. In a search engine, you take the data in that content field, you split it apart, you tokenize it into individual terms, and you actually use the terms as the key into this inverted index. Think of it as like a giant hash table, where every keyword goes in as the key, and then the documents that keyword is found within become the value that it's mapped to, along with some other information like position in the document. What that means is that you can put billions and billions of documents in the system, and whenever I want to do a keyword search, it's just a lookup in the inverted index and the hash table effectively, which means it's lightning fast. So if I want to run a search for Apache Solar, all I have to do is look up the entry for Apache, get the document set, look up the entry for Solar, get the document set for that, do a set intersection, and I've got my response in milliseconds across millions or even billions of documents, which that's how search engines are fundamentally able to be so fast. One of the important things in order to get there that you have to do is take that content and break it up into pieces. So I'm not going to spend a lot of time on this section, but basically just to say in Lucene and in Solar, there's a really, really rich NLP framework for tokenizing, tokenizing stemming, removing accents, dealing with pretty much every language you can imagine. There's over 100 languages supported. And so for things like, I've got some examples here for Arabic, Romanian, Persian, Japanese, Hindi, Greek, etc. From my book, Solar in Action, you can see that there's really sophisticated ways of leveraging building blocks and components. And even if you're not using Lucene or Solar as your search engine, a lot of you guys are using Scala and Spark. So just as a heads up, LucidWorks is open source, an integration between Solar and all of the tokenizers and analyzers and everything that you can use directly in Spark if that's more your style to break text apart. Just please don't do text.split on white space. That's like the most simple thing you could do, which is where most people start. There's a lot better toolkits out there. Once you've run that search, like we had earlier for Apache Solar, and found all the documents that match, the question then is, how do you rank those documents? So this is the classic Lucene similarity calculation, which there's a lot of pieces here, but at the end of the day, there's two things on here which almost everyone in this room is going to immediately identify, which is TF and IDF. Term frequency is a measure of how well a term describes a document, and inverse document frequency is a measure of how important the term is overall, or how rare it is. So if somebody were to run a search for something like an experienced solar development team lead, they would be really, really unhappy if the top results that came back were the documents that had the word "an" in it the most times. That's not at all what you're looking for, right? The most relevant word here is solar, and the reason it's the most relevant is because it's the most rare. It's the most unique. Therefore, the search engine using TF and IDF combined is able to score every term in a query based upon all the documents that match, and then return all the documents in ranked order. The default in Lucene and Solar as of Solar 6 is BM25, which has been around for ages. It's basically another variation on TF-IDF that also gives you the ability to set sort of an upper threshold for how much TF can contribute towards your score, as well as to weight the document length as part of the score a little bit better. So I won't spend time on it. These slides will be available later if you want to dive into them. But this is the sort of fundamental way that text scoring happens in most search engines, some variation of this TF-IDF concept, which is great. Out of the box, if you know nothing about your domain and all you have is a bunch of data and you just need to search it, this is a good place to start. But it completely ignores domain-specific knowledge. So, for example, if I'm running a news search website, the things that are probably the most important to me are the popularity of the articles and people clicking on them and how fresh they are. I don't want to be showing news articles from a week ago or a month ago. I want to be showing news articles from at least the last day, maybe even sooner. And I want to show the popular ones. For restaurant search, you might care about things like geographical proximity and price range. For e-commerce, likelihood of a purchase is probably key, et cetera. For a movie search, more popular job titles are going to be more relevant than less popular job titles, and unfortunately, movie titles. Unfortunately, a lot of movies actually share the same title, so you really want to get that right. If I search for Beauty and the Beast right now as a movie, I really don't mean the old animated cartoon. Like the popularity and the context is just not there. So, moral of the story here is that TF-IDF, while a good tool, really can't hold its own against domain-specific relevance factors. So when someone's building a search engine, really understanding the domain and modeling relevancy in the query is key. So a couple ways you can do this. This is an example for the news website I was just referring to. In Solar, this is just a query to the search engine. You don't have to write any code for this. But I'm basically saying, I want to weight 4 things in my relevancy calculation: the query match, TF-IDF, the distance from me, the publication date of this news article, and the popularity of the article. And each of them basically gets a fourth of the weight. This is something you can do really easily with Solr, and move around and play with things and very easily test the results of this kind of relevancy tuning. Similarly, with a restaurant search website, in this case, I'm basically weighting the distance from me right now as the most significant factor. 50% of the relevance comes from that, 30% comes from the keywords I typed in, and 20% comes from the category associated with the keywords I typed in. So if I search for filet mignon, it's gonna limit me to fine dining, not just filet mignon, but it's only gonna show me restaurants that are really close to me, because I don't want, frankly, a nice fine dining restaurant in San Francisco to be offered to me if I'm looking for a meal tonight. That just doesn't make sense. So all of this is also very powerful, but it feels like a lot of work. I mean, I showed you a slide. You didn't have to do any work, but I had to think really hard about what that was going to look like. And you imagine, tons of relevance engineers trying to figure this stuff out day in and day out. So the question is there a way to make this easier so that people don't spend years trying to craft this exactly right relevancy formula, which frankly will work in some cases and not others. And so that's where the idea of reflected intelligence comes in. And I define reflected intelligence as leveraging previous data and interactions in order to improve how new data and interactions should be interpreted. And so at LucidWorks, we tend to talk about this in terms of the 3 C's. This is content, the keywords and other features in your documents, collaboration, or how others have chosen to interact with your system, and context, which is information that's available about your users and their intent. Some examples of reflected intelligence, you've seen many of these, are recommendation algorithms, building user profiles from past searches, clicks, and other actions, identifying correlations between keywords and phrases, generating ontologies, ideally automatically, from logs and content, relevancy judgments, learning to rank, which is building models to automatically learn which features are important and weighting them accordingly, not having to do that manually like I showed you a minute ago. Discovering misspellings, synonyms, acronyms related to keywords, disambiguating, like driver, the word I mentioned earlier. How do I know what the meaning is in any given context? And just basically learning what's important in your content. So as a thought exercise, I've got some profiles here that were created. This is somebody who's potentially looking for a job. So this is an example from Solr in Action. I've got John here in Boston. He's a sales manager looking to do something else. But I'm going to focus in on the one at the bottom, which is Jane. She is a nurse educator in Boston seeking between $40,000 and $60,000. I might know that from her profile. I might know that from learning a model of what she is looking for based upon her previous interactions. But let's just assume that I have this profile of Jane. What can I do with that? Well, what if I turn Jane and her profile into a query? So this isn't a keyword query like you would typically think for a search engine would receive, but instead I'm basically saying, all right, I know the job title she's looking for is nurse educator. So if it's a perfect match, I'm going to give it a high boost, high relevancy boost. If it's not as good of a match, if it matches at least one of the words, I'm still going to weight it reasonably high. But then I'm going to search for Boston, Massachusetts. And if it's an exact match for Boston, I'm going to give it a high boost. But if it's at least in Massachusetts, I'm going to give it some relevancy weight. And finally, this thing at the bottom is basically saying, if I match the salary between $40,000 and $60,000, also, add a factor of 10 to the boost. So, it's a very fuzzy ranking calculation, but, again, Jane, nurse educator, Boston, $40,000 and $60,000. If I run that against my sample job set, what do I get back? Well, the first match is a clinical educator, good, in Boston, great, salary between $40,000 and $60,000, bingo, just what I wanted. It's not a perfect match on the title text-wise, but this is the best match of the 3. The next one, I've got a nurse educator, great. Braintree, well, it's not Boston, but it's really, really close. And it's between $40,000 and $60,000. Awesome. The next one, nurse educator, great. Brighton, again, not Boston, but close enough. Outside of my salary range, but it's still a match. And so that's what the search engine does well, is this fuzzy matching. What you'll note here is that Jane didn't actually type any of this into the system. We just knew information about Jane and were able to pass it to the search engine as a search. What did we just build? A very lightweight content-based recommendation engine, just by passing a query. A lot of people tend to think of recommendation engines as this entirely separate thing from search, but it's really just a long spectrum of information retrieval. And oftentimes you can do the same recommendation algorithms in search that you can do with some offline system with a lot more flexibility, as you see, being able to easily tune the parameters in the query to make changes without having to write code. So one other thing you can do with the search engine is collaborative filtering. You can, for example, on documents, stamp them with the users who've liked them or purchased them or what have you. And then once that's indexed into Solr, when a user comes in who's looked at document 1 and document 4, I can basically tell the search engine to facet on those documents, get me all the users, count them up, and say, okay, this is the weighted list of users that likes these documents. I can then take those users, pass them as a query to the search engine. Again, not a keyword search. This is a behavior search in this case, but the behavior stamped on the documents. Run that as a query, and voila, I've got my collaborative filtering algorithm by basically running a search. You can also, that works okay if you don't have a ton of signals or actions on the documents. When you start scaling up, you really want to do some sort of matrix factorization, like you would typically do in a recommendation algorithm. That's something that we've got built into Fusion, leveraging Spark and using an ALS algorithm to generate user item and item recommendations. But this can all be powered off of the search engine with maybe some metadata computed offline. Which gets us, again, to this idea of feedback loops. What we really want to build here is a system where the user runs a search, sees results, takes an action on those results. We record those actions, run some aggregations and computation on them, feed that information back into the system, which enables it to improve the searches for the next user, who then runs a search, and the whole cycle repeats over and over. So the engine is constantly growing and learning and getting better. So I want to show you a quick demo. This is going to be a Fusion demo, leveraging Solr and Spark. Let's see, give me 1 second. All right, here we go. So this is a website. It's just like an example kind of e-commerce website we use for demos. I'm going to put Lenovo laptop in here. This is using just TF-IDF, and what you'll notice is that the top results that came back aren't actually very good. There are a bunch of batteries for Lenovo laptops. Not what I meant, but I do see some good results in there, so I'm going to try something else, which is Big Bang Theory. Type in Big Bang, these results don't look very good either. Again, TF-IDF, it has no notion of what I intended, but let's clarify it. Nope, still not great. There's some, okay, it's better, but still not great. Let's try iPad. Again, there's iPads in there, but the top things that are showing up are cases and AB components. Obviously, I chose these examples intentionally because they're bad examples. Not everything looks this bad. But so in Fusion, one thing we're able to do, we have this concept of query pipelines. So over here on the left, you see a whole lot of different query pipelines. These are different relevancy algorithms and things that I can try. The one I used a second ago was just my default relevancy algorithm, which just does TF-IDF basically, maybe some field boost. I also have this one right here called my signals pipeline, which takes all of the user interactions that were previously entered. It takes the aggregation of those and actually uses those to boost documents that were clicked on more often based upon the query. So I'm just going to flip it right here from my e-commerce pipeline to use my default pipeline to use my signals pipeline, and save that. And now if I go back to my website and run the search again for iPad, let's just do that one. Voila, results are much better because it's actually taking into effect what users looked for before and what they clicked on. If I go back now and type in Big Bang, notice that all of the results look good, just like I would expect. And I even got rid of the weird one-off SKUs that didn't have pictures because people apparently don't buy those. And then if I go back to the first one, which was the Lenovo laptop, then let's see if the batteries are gone, and they are. So this is, again, by using what users click on to influence the relevancy, this is allowing us to have better results. And so in this case, you've got kind of a grid laid out here. You can see my original query on the left, which was just TF-IDF, and then me sort of combining that with relevancy functions for signals, and then my recommendations based upon the things that came back as well. And the important thing to note here is that as you look at those results, the important thing to remember is nobody had to program the system to do this. This is an algorithm that just leverages signals, and it's a feedback loop, and it's constantly getting better. And the nice thing about this is when we give this to customers, just to give you one example. So this is Red Hat. They have a customer basically question answer portal. You know, when they went live with signals, they went from about a 20% click-through rate to about a 60 or 70% click-through rate. Almost overnight. You see that big jump, and since the system continues to learn and get smarter over time, that the trend just kept growing until it hit a saturation point. We've also got a top 10 retailer who plugged this in and very quickly got 20% increases in checkouts, which is millions and millions of dollars by just letting the system learn on its own and not having a bunch of people trying to tune the stuff manually over time. Sometimes, though, you might have content that doesn't allow you to actually use the data itself. Like if you think of a news website or a job search engine where the data is constantly changing, it doesn't stay around long enough to use those signals. So in those cases, it's better to use something like learning to rank, which is using the data to train a ranking classifier to learn features, and that way when you have new content coming in, that new content doesn't have the cold start problem where it has to be clicked on a bunch before you can start recommending it. You can actually just, based upon the features of the document, show it. So I'm going to show you really quickly. In Solar 6.4 and beyond, learning to rank is built in. So just as a sort of quick demo here, I included steps here for anyone who gets the slides and just wants to play with this. Basically, if you run these 6 sets of commands, you've just started Solar, indexed documents, built a learning to rank model, and deployed it, and you can see the results. So it's basically, pull downs, build, run Solar, run a basic search for iPod, enter some relevancy judgments. This is just a linear model here, but you can do SVMs or Lambda Mart or what have you. You train the model, upload it to Solar, and then it works. So in this example here, I'm searching for iPod. Notice the third result is an Apple iPod, and the first 2 aren't. If I then take my user relevancy judgments, some of these coming from my click log, some of these coming from human judgment, and I'm just faking it here for purposes of a demonstration, but if I basically say, hey, that iPod really is relevant for that query, I then train and upload my model, run the search again, voila, I now have Apple at the top. And it wasn't that specific document that got the boost, it was the system learned the features that are in that document that made it relevant and across all of your documents. So it's a really cool, building a ranking classifier and having the search engine use it to re-rank documents is really powerful. And for the sake of time, I'm gonna just kind of skim over the semantic search stuff. But in order to really understand your domain, you have to have a taxonomy or an ontology. There's lots of ways to build that. A common way is using learning to rank. And this example I gave you earlier, these related keywords at the top actually came from mining query logs. So you can find related keywords that way as well. Word, Devet, Glove, or some common algorithms. Once you have those entities, you sort of can index them into the search engine. And Solar has this open source project called the Solar Text Tagger that allows you to do entity extraction on those. Once you've done that, there's another open source project called the Probabilistic Query Parser, which allows you to basically take in something like senior Java developer Hadoop, parse that out and not see it as individual terms and tokens, but to actually understand that senior Java developer is a phrase and Hadoop is a phrase and treat them accordingly, which makes the search engine much more relevant. I'm going to skip over these slides here. And the last section here is query augmentation. So once you've run your search and you've identified the terms and phrases that are domain specific as part of your search, there's a couple of things you can do. One thing you probably want to do is take those terms and expand them out to include other related terms, sort of a concept search as opposed to an individual term search. So if you have a taxonomy you've built internally in ontology, there's a Solar RDF project you can use to basically find related terms and phrases. Otherwise, there's an interesting thing that I worked on with the team at Career Builder a while back called the Semantic Knowledge Graph, which is open source, which allows you to basically run a search, whereas normally a search engine, you run a keyword search and find related documents. This allows you to basically run a keyword search and find related keywords. And so you can basically traverse that graph, see which keywords are the most relevant for any given topic, and then insert those keywords as part of your query to do a conceptual search. And this will be in the slides. You guys can take a look at it later. But at the end of the day, you take the like in this example right here, I ran a search for detergent for clothes. Contextually, using something like the semantic knowledge graph, I can understand that detergent for clothes is laundry detergent. Laundry is, a related term in there, so I run a concept search, which gives me much better results, as you can see over here on the left with laundry detergent versus dishwashing detergent on the right. And as a last slide here, one other thing you can do with this, once you've got that taxonomy of terms, you can then take a document, extract the entities, pass them to this graph and score them. And so this gives you, it's a really cool data science tool where you can basically have a summary. So this is a job description of a big data engineer. And notice on the right here that it has been very neatly summarized as data engineer, Hive, Pig, Hadoop, MapReduce, NoSQL, et cetera, which is a nice, clean, ordered list based upon how relevant each of those terms was within the document that was found. So I told you guys it would be a bit of a whirlwind, nice quick overview of a lot of interesting ways to improve search relevancy. But we basically walked through, the sort of bottom of the spectrum with basic keyword search, talked about taxonomies and extraction and how you can generate those automatically. Talked about query intent, semantic query parsing, and concept expansion, using learning to rank and signals for relevancy tuning, and ultimately how tying all those things together, in particular the signals and things based upon the signals allows you to actually have the system self-learn, and like we've seen with our customers, really drive significant value for your company. So that's my talk. I'm Trey Grainger, and thank you.
Thank you so much, Trey. Trey ran out of time. That's why you can ask him all the questions during the break
Ask me on Twitter.
or lunch.